Welcome to GeoEnergy21's session about improving cost efficiency and achieving successful projects. My name is Korneel van Meer. I'm happy to have you on board for this short talk on new applications for geothermal developments. Unlike Norway, the Netherlands doesn't have the geographical luxury to build hydropower storehouses. So to move away from coal and fossil fuels, the Dutch rely on wind, solar, and in the last decade or so also geothermal energy for district heating is picking up. So with a temperature gradient of approximately 30 degrees Celsius per kilometer and reasonable permeabilities, geothermal energy can play an important role in the energy transition for the Netherlands. This potential is well recognized, even so that in a collaboration between branch organizations and the Ministry of Economic Affairs and Climate Policy, a master plan geothermal energy was crafted in 2018. In there, it is foreseen that geothermal energy can account for 23% of the total heat demand in the Netherlands, so 200 petajoules, where 1 petajoule accounts for approximately 20,000 households. To realize this ambition, approximately 680 doublets need to be drilled in the next 30 years. At Huisman, we see it as our mission to accelerate the growth of renewables. With a long history of designing, manufacturing and servicing innovative equipment for the energy sector, we decided to put our expertise to work in order to drive up the economic feasibility of geothermal plants. Today, I'm going to show you 3 technologies to reduce drilling risk, to cut down both installation and running costs, and to combat well corrosion issues. First, the digital mudlogger. Second, directional casing drilling. And third, composite casing. Composite tubulars, in this case used as casing. These various technologies are in different stages of their development, from proof of concept to fully tested and validated. Yet all of these will be deployed together in a demonstration project by the end of this year at the Center of Sustainable Geoenergy, a facility from TNO, the Dutch Organization for Applied Scientific Research. Let's jump right into it. The digital mudlogger. While drilling, a lot of information on the subsurface as well as from the drilling process itself travels to surface via the drilling mud. Like the name already suggests, the digital mudlogger seeks to digitize and automate the typical mudlogging activities. So the examination of drilling fluid, and in this case specifically of the rock particles contained therein. Collecting this information in a structured and uniform way across projects will help build valuable data sets that can provide insights into the geostrata that you're about to drill in your next well or project. Furthermore, the shape and the volume of cuttings and cavings over the shaker bed gives you a direct indication of your hole quality and whether you're working with the proper drilling parameters. So all this information is available, we just have to find a way to detect it, to store it, to analyze it and to present it in such a way that it generates knowledge on one side and actionable data for the driller on the other side. Here we see a system overview of the digital mudlogger. So a combination of sensors is placed directly above the shaker and both hyperspectral and visual images are generated. All this hyperspectral and visual data can easily be time synchronized with other data from the rig. In order to draw basically a full picture of what's going on. So information like pump rate, standby pressure, weight on bit, mud weight, ROP and so on can all be synchronized. Where this is possible today, in the future we foresee that these digital mudlogging results can even be fed back into the control system of the rig to support in the optimization of drilling parameters. Now, what is the next step? Where to use all this data for? Well, the hyperspectral data can be used to determine mineralogy, so we can work towards a representation of the wellbore showing the lithology. Furthermore, by using computer vision software on the visual camera data, particles can be categorized by their shape, size, volume, ultimately to determine whether you are dealing with cuttings or cavings and if your wellbore is stable and drilled with the right settings. The second technology is directional casing drilling. So we know conventional drilling, where we drill with drill pipe, you trip out the bit and run in casing and cement it in place. And then there are several levels of casing while drilling. So level 1, basically reaming casing into a pre-drilled hole. Level 2, you drill with the casing and it's a bit that you drill through in a later stage. And level 3, where you work with a retrievable bottom hole assembly. So basically the whole bottom hole assembly, the bit, the reamer, the mud motor, MWD, maybe the LWD, are all connected to a lockdown device, and this lockdown device latches into the casing. Now, when you want to drill directional holes with casing drilling, mostly a mud motor and bent sub is used. So you have to slide basically when you're building. So the casing string is stationary and only the mud motor rotates the bit, and then you slide into a certain direction. Now, what we are going to talk about is level 3 plus, so to say. So it's retrievable bottom hole assembly, but then with RSS functionality. This is made possible by combining Huisman's Enhanced Casing Installation System, ECI, that's the device that locks the BHA into place, with Huisman's Synco drill. This is a fully mechanical downhole tool that points the bit into the desired direction, even when the casing string is continuously rotated. So typically what you would expect from a conventional rotary steerable system, but then way less complex and thereby much cheaper. So Synco drill is a low-cost RSS specifically for casing while drilling. Why would you want to drill with ECI and Synco drill? First of all, you have an immediately cased hole during drilling. This eliminates hole stability issues and the risk that the casing doesn't get to bottom. Besides, you don't have to trip in and out the drill pipe. This not only is better for your hole, but also saves valuable time and mitigates the need for hazardous pipe handling activities on the drill floor. For today, it would go into too much detail to go through all of the components and the control principles of the Synco drill system, but what can be said is that it's a simple, fully mechanical downhole device that enables automated directional drilling, and that its steering performance is consistent regardless of the formation strength. The third and last technology that we will discuss today is HCT, or Huisman composite tubulars. Corrosion and scaling of wells is a major concern for geothermal operators. Formation brines are not only very salt, they can contain huge amounts of salt, but also dissolved gases like nitrogen, hydrogen and especially carbon dioxide make it a very aggressive substance. This combination of being an aggressive substance combined with high fluid velocity and turbulence will remove any protective layer. So it's detrimental for steel tubulars. Mostly it would be impossible or way too expensive to stop all corrosion and scaling. But by moving away from metallic materials, you can tackle these issues at the core. We have developed a robust composite tubular system specifically for downhole conditions. This provides a fully composite and thus corrosion resistant flow path. Furthermore, you don't have any scaling, so where dissolved salts attach very well to steel surfaces, that is not the case for composites. So the salts basically don't have the chance to precipitate on your material. The connection is very slender, so in order to maximize the internal flow area and minimize pump losses. And last but not least, composite is significantly lighter than steel, so thereby allowing for smaller and lighter installation equipment. This step change is made possible by a merit of two novel technologies. First, the uniquely strong and robust composite thread connection. On the left picture, on that image, we see the pin end of this connection. the middle image shows an actual cutout of the assembled max flow connection. And this joint can handle high compression, tension, burst and collapse loads. You can even make it up and break it out to full torque a few times without it getting damaged or losing performance. Secondly, of course, the composite pipe itself. The pipe body is made out of glass fiber and epoxy polymer. And due to the unique manufacturing process, no air is trapped in the matrix. So only reinforcement and resin and no air bubbles that weaken the material. We have been developing and qualifying this product for the last 3 years. And now it's ready for first deployment. Where during development of the current product we mainly targeted low enthalpy geothermal applications, we see that this composite technology can bring value to many other fields and use cases, like for example in the oil and gas, solution mining or thermal energy storage. Another feature of composite is that it's non-magnetic and thereby transparent for logging tools. So you can actually look through the casing. And this can be useful for example, reservoir monitoring or for housing an LWD inside the casing during directional drilling. While designing solutions, we strongly encourage to take the full service life of the well into account, so optimizing the overall CAPEX and OPEX. By doing so, it is seen that in geothermal applications, composites can bring a sustainable solution and significantly reduce the cost for example, inhibitors, pump energy cost, and well integrity related non-productive time. As mentioned in the beginning, all the 3 technologies discussed today will be deployed in a demonstration project by the end of this year at the Rijswijk Center for Sustainable Geoenergy. This is a field lab run by TNO where geothermal innovations can be tested in full scale, and they will realize a test well for research on geothermal energy, and as a part of that the shown technologies are deployed. So the measuring and data gathering functionalities of the ATEX-proof digital mudlogger system will be demonstrated. The ECI synchro drill system is used to drill the 958-inch casing section. And 4 sections of Huisman composite tubulars will be installed as a part of the final casing string. In conclusion, over the last couple of minutes we've seen 3 key technologies that will help to drive up the economic feasibility of geothermal projects. Thank you so much for joining me. We have a few minutes for discussion. Feel free to join. In any other case, if you would like to find out more, please visit our website or drop me a line.